Welcome to structural dynamics class. In this class we will discuss about response spectrum. Now, what is response spectrum? Response spectrum is a plot of maximum response of linear single degree of freedom oscillator for a given component of earthquake ground motion. So, on x axis we have natural period and on y axis we have response quantity. So, this response quantity can be maximum displacement, maximum velocity or maximum acceleration. So, we can plot response spectrum for displacement, for velocity and for acceleration. Now, what is this concept all about? Let us look at the slide and understand. So, here you can see three idealized structures. So, first structure has mass 1, stiffness 1, and then this structure, if we calculate natural period of this structure, it will be T1. So, T1 is equal to 2 pi under root M1 by K1. So, that is T1. Now, second structure is again idealized structure, mass 2 and stiffness 2, T2 is the natural period of this structure. So, natural period of this structure is calculated by T2 is equal to 2 pi under root M by M2 by K2. And third structure M3, mass 3, stiffness 3. In the similar manner we calculate natural period of this structure. Now, what response spectrum gives is, if natural period of T1, T2, T3 all are same, then for given component of earthquake ground motion, maximum response is same for all the oscillators. So, that means no matter whatever the structure's mass and stiffness be, if natural period is matching, then response spectrum says that maximum response is same for all three oscillators. So, the maximum response of linear single degree of freedom system to any given component of earthquake motion depends only on natural frequency or natural period and damping. So, only these two quantities it is dependent. So, now I would like to show you a small video clip, okay, so explaining the concept of response spectrum. Let us look at that. So, if we look at this small experiment, okay, so in this one there are 4 oscillators, 4 idealized single degree of freedom systems, or we can call it as 4 buildings. So, from left side the third building is the tallest building, and then on the right there is lesser than that, okay. So, let us take this as like one period of this building is some value, and then this has lesser period. So, tall buildings will have more natural period, short buildings will have less natural period. So, the second one is having slightly lesser natural period, and then this first structure, the left side structure and the second structure, both are matched such that their period is same. So, that means what, lengths of the buildings are slightly different, but mass is adjusted such that both natural periods are same. So, now if we excite all these buildings to some frequency, what is going to happen? Let us look at it. Now, as you can see, slowly varying acceleration, that means slowly varying force is applied. So, because of which that natural frequency is matching with the natural frequency of the tall building. So, that is why tall building is vibrating violently, severe motion, severe displacements. And then on the same ground, like if we increase the frequency of the ground motion, then this tall building is not having that much amplitude, but the second building is having, that is the last one, right side building is having more. And then if we increase the frequency of this one, excitation, so this first and second buildings are having more frequency, sorry, more displacement. In the video what we have seen, first tall building, so for slow vibrations tall building got affected, and if when we increased the oscillation, that is the period of oscillation, when we increased the frequency, then second building started vibrating, and after that first and second, that is first one, left side one, and the second from the left building vibrated. So, from this we can understand that not all buildings will fall down due to earthquakes. So, the earthquake the frequency of earthquake and if the building's frequency, if they match, then a peak, that is the resonating condition, might occur. So like that, so the concept of response spectrum says that if we know the natural period of the building, what will be the maximum response of that building to a given component of earthquake can be known from response spectrum concept. So now this response spectrum is extremely useful concept in earthquake engineering research and in applying seismological knowledge of strong earthquake ground motion to the design of structures. First proposed by Hugo Benioff in 1934, and Biot extended its application to earthquake engineering in 41. Now uses of response spectrum, where we use, for engineering purposes, we are not especially concerned with the time variation of the response parameters. Rather what we need is maximum responses. So that is extreme value that conveys the crucial information. Now they are related to maximum forces, maximum displacement and maximum deformation that structure must be able to endure. So we need maximum values. So hence response spectrum is needed. So now how do we construct this response spectrum? So what we do is, like we first take a ground motion. As you can see here, this acceleration is given, ground motion acceleration, and then we put a suite of oscillators, linear single degree of freedom oscillators with some fixed damping value. So let's say 5%. So T1, T2, T3, T4, T5 like that, so on. So usually oscillators will range up to a period of say 0.1 seconds to say 4 seconds or sometimes 6 seconds oscillators. And then we already studied the how to find the response of structure to a given random motion by using numerical techniques. So we can use either Newmark's technique or this central difference method, and then find out the response of this linear single degree of freedom oscillator. So second one, third one, like that, all oscillators response we find out. So the response spectrum is a plot of maximum response of linear single degree of freedom system oscillators as a function of natural period. So if we put that, okay, response quantity can be either displacement, velocity or acceleration. Now if you look at this one, okay, so this has three structures. So structure of natural period 0.5 seconds and damping 2%, and second structure is structure of 1 second natural period and damping value as again 2%, and third structure is natural period as 2 seconds and damping percentage also 2. So for this three structures we are giving L centro ground motion as input. So when we are giving L centro ground motion as input and using some numerical technique, either central difference method or Newmark's method, we get the time history of this structure, time history. And then similarly the second structure we get time history, and third structure we get time history. So in the first structure, maximum displacement as U max is equal to 2.48 inch, and in the second structure maximum displacement is 6.61 inch, and in third structure for the same earthquake the maximum displacement is U max is 8.84 inch. So this maximum displacement is maximum value at any point of time in this time history response. So here also maximum value at any point of time, maximum value at any point of time. So one should observe that these maximum values are not occurring at the same time in all the oscillators, all the structures. So they can occur at any different point of time. So now what we do is, this natural period of this structure is 0.5. We put 0.5 on the x-axis. Natural period of this structure is 1 second. We put 1 second on the x-axis. And natural period of this structure is 2 seconds. We put 2 seconds on. So corresponding displacement values we plot on y-axis. So this is a point. This is another point. Another point. So now what we do is, we take many more structures like this and then plot this curve. So this curve is called response spectrum of displacement for L centro ground motion and damping assumed as 2%. So this is the concept of response spectrum. This is how we construct response spectrum. You can see here, if we calculate the maximum response of a range of values of frequency and damping and portray the results graphically, we then have a spectrum chart that shows maximum response of all possible single degree of freedom systems to that component of earthquake. Now once we have this kind of response spectrum developed for an area, then in that area whatever kind of building is coming, say single story building, 2-story building, 3-story, 20-story building, 30-story building. So what we need to understand is, before design of that building itself, we can calculate the natural period of that building and put on the x-axis and check the maximum displacement value. Now that is the maximum displacement which that structure will undergo in the event of this earthquake or similar earthquake, okay, if they are having the same frequency components in it. So this is a concept of response spectrum. It is extremely useful concept in the application of earthquake engineering. Okay, now you can see this one. This response quantity can be either displacement or velocity or acceleration. So this A chart is telling displacement, B is telling velocity, and C is acceleration. Actually these three things are linked also. So all three responses can be shown in one plot, which is called tripartite plot. So we will discuss in the subsequent lectures about how to construct this tripartite plot. But let me show you what is tripartite plot. So this tripartite plot is, on the x-axis we have either natural period or natural frequency. On y-axis you can see velocity. So that means what? Velocity of this structure can be measured, velocity response of the structure can be measured if we know the natural period or natural frequency. So we know natural frequency, say 0.5 hertz. So then we directly go to that, and here we have four plots. So each one corresponding to one damping value. So damping 0 is there, damping 2%, damping 5%, and damping 10%. So let us take say 0 damping. So 0 damping is the last curve. So we go there and hit that curve and then directly come here and read this one. So please note that this plot is in log scale. So we need to read that like that only, read it like that only. And now how to get displacement from this one? From the same point, you can see on the 45 degrees line here, we can directly drop like a point or a line perpendicular to this 45 degrees line. Then you measure displacement. You can see values here 0.1, 0.2, 0.5, 1, 2, 5 like that. So we can read this is the displacement value. And similarly on the other direction, again 45 degrees, okay, plus 45 degrees and minus 45 degrees lines, we can go and drop another perpendicular line and then read acceleration value. So this axis is telling acceleration 0.02, 0.05, 1, 0.1, 0.2, 0.5 like that. So we can read the acceleration here, we can read displacement here, and we can read velocity here. So that is how we can read in one plot all three values. So that is called tripartite plot. So how to construct this tripartite plot we will discuss in next lecture. Now let's solve one problem. Okay, let's use this response spectrum and find out the response quantities. So this example says that consider a structure shown in figure. So this figure where mass of the system is 2000 kg and stiffness value is 80 kilonewton per meter. Let the structure be subjected to ground motion whose spectrum is given. So spectrum is known to us. If damping is 5% of critical, then what are the spectral quantities? So spectral quantities means we need spectral displacement, spectral velocity, and spectral acceleration. We will discuss about why we are calling pseudo spectral acceleration or pseudo spectral velocity in the next class. So this is spectral displacement, this is pseudo spectral velocity, pseudo spectral acceleration. Now for that we need natural period of the building. So natural period of the building, that is Tn is equal to 2 pi by omega n. So where omega n is a natural frequency which can be calculated using stiffness and mass parameters. So stiffness is given to us, that is 80 kilonewton per meter. So I substituted that 80 kilonewton per meter here, and then mass is also given 2000 kg. So the result is 6.324 radians per second is a natural frequency of the system. Now I substitute that 6.328 here, 2 pi by 6.328, that is 1 second. So natural period of this system is 1 second. So now for 1 second, these are the corresponding displacement values, velocity value, and acceleration value. How did we get it? Now let's look at this chart. So what I did is, so I took that frequency, the natural period is 1 second. So that is frequency is equal to 1 by t. So 1 by 1 is equal to 1 only, 1 hertz this is. So this 1 hertz frequency, with this using this one, we are given 5% damping. So second line, second plot. So from there I can directly go to like y axis and measure the velocity. So velocity is 25 inch per second here, and if we convert in SI system, that is 63.5 centimeters per second, this is velocity. This is pseudo spectral velocity. And then from the same point on the curve, we drop like on plus 45 degree axis. So we hit this point. So that is displacement. So that is 4-inch displacement, that is equal to 10.16 centimeters. And then on minus 45 degree axis, if we drop, that is perpendicular line, we get acceleration. That acceleration is 0.4 g, that is 392 centimeters per second square. So that's how we get spectral displacement, spectral velocity and spectral acceleration, 3 values. So we can get these spectral values. Then it is very important for us to calculate the maximum forces. So what we got from response spectrum chart is spectral displacement, spectral velocity and spectral acceleration. So actually what we want is, for designing of a building, we need forces. So we need base shear and then the distribution of base shear over the height of the building. So how to calculate base shear and how to calculate base moment? So let's discuss that. So quite often engineer is interested in finding maximum force that the structure experiences during earthquake. It can be written in terms of maximum displacement of structure with respect to base. Now if you look at this, force is mass into acceleration, and the same force as a reaction here, that is called base shear. So we can calculate base shear and also base moment, because force is acting at h from the base. So how do we get that force? So force is simply F is equal to K, stiffness multiplied by maximum displacement. So this maximum displacement is what? This is a spectral displacement, what we get from response spectrum plot. So at base we can, that same thing, it is VB, that is base shear, is equal to K into U max, K into U max. So and then base moment is MB is equal to F, force into lever arm, that is H, VB into H. So hence we can call this directly as K multiplied by spectral displacement, K multiplied by spectral displacement multiplied by H. Then calculate maximum base shear and maximum base moment of structure in a given example, example 1. So base shear can also be calculated in another manner, that is mass into acceleration. So what is that acceleration? Pseudo spectral acceleration from the tripartite plot or response spectrum plot for acceleration. So mass given is 2000 and the acceleration value is 0.4 g. Yeah, 0.4 g is the acceleration value. Here you can see 0.4 g. Then if I multiply these two, I get like 7.48 kilonewton is a base shear, maximum base shear. And similarly, if I multiply that with height of the structure, then I get 23,544 kilonewton meter as base moment for the structure. So these base shear value and base moment value are required for the design of this structure. Now how do we construct this acceleration response spectrum? Why we are calling pseudo, I will discuss in the next class. Construction of acceleration spectrum. So we have linear single degree of freedom system, and the equation of motion for that linear single degree of freedom system is mu double dot plus cu dot plus ku is equal to applied force. That applied force is coming from acceleration. So that P of t is equal to mass into acceleration, and then this is the response. Now what we do is we get the response for many structures like that, okay, and then use the concept of this spectrum. So for given L centro ground motion for different damping values, we have plotted this response spectrum for acceleration. You can see this one, black one is for 0.15 15% damping, and red line is for 10% damping, and blue line is for 5% damping. So you may note this one, as damping increases, it reduces the amplitude value at the same natural period. Okay, it reduces the amplitude value. So this is a response spectra for various damping values for a given component of earthquake. In this example, we have used El Centro ground motion. Now, how do we construct design spectrum from that? And but what is the design spectrum? So the plot what is given in IS 1893, that is criteria for earthquake resistant design of buildings. So in that, the plot given is called design spectrum. It is not response spectrum. So design spectrum is a plot which comes from response spectrum. So what is design spectrum? Okay, so it accounts for issues that have bearing on seismic safety, something like overstrength, redundancy and ductility. So these three things are it accounts for that, these things. And the design spectrum must be accompanied by what? Load factors and permissible stresses, damping to be used in the design, method of calculation of T, and type of detailing for ductility. So now how do we get this design spectrum? So after getting suite of response spectrum or spectra for different ground motions, what are possible or what are likely to occur in that area, so we get response spectra for different ground motions. So now what we do is, from that, okay, we do a averaging kind of thing. So this averaging is called statistical averaging. So this the procedure is detailed procedure is given in the Newmark and Hall textbook. So what we need to do is, this design spectrum will be smoothened out. So something like we have many spectra, say T, this is, let's say, acceleration. So we get the average response spectrum. So something like, say, one average response spectrum, something like this. So but in design spectrum, the issue is what, if we use this average response spectrum, the issue is, like, if there is a mistake in calculation of natural period for any structure, okay, instead of this one, if it is another value, so then suddenly at that point response may be peak. So in order to remove this kind of discrepancies, the plot is smoothened. This average spectrum plot is smoothened by using coefficient. So if it is for acceleration for 2%, so this coefficient is used. For velocity and for displacement, these coefficients are used, and then these limits are set. So this one is natural period on the x-axis, and PSV, that is velocity, pseudospectral velocity, on y-axis. So these control points are given at 1/33 seconds, 1/8 seconds, 10 seconds and 33 seconds. So these points are given, and these points, this middle point is achieved by using trial and error method. So this region, this region is acceleration sensitive region, this is velocity sensitive region, and the after this one, this is displacement sensitive region in the design spectrum. So this is a design spectrum what we use in IS 1893, that is the criteria for earthquake resistant design of building. So here this spectrum is given for different types of soil conditions. One is type 1 rock or hard soil, and medium soil, this is hard soil, medium soil and soft soil. So obviously soft soil response is higher, so that's why this coefficient values are higher. So in summary, what we have discussed in this class. So in this class we discussed the concept of response spectrum, what is response spectrum, and then what are the advantages of response spectrum, and how do we construct response spectrum, and how do we use this response spectrum, and briefly we have discussed concept of design spectrum. Okay, so in tutorial detail you will be explained one example problem.